In 2006, something quiet but historic happened in astronomy. Pluto, once known as the ninth planet of our solar system, was reclassified and moved into a new category, a dwarf planet. A small, distant world of ice and rock suddenly lost its planetary status and faded from mainstream attention. For many, it became an overlooked object at the edge of the solar system, cold, distant, and seemingly inactive. A leftover fragment from the formation of planets. The decision sparked debate across the world. Scientists discussed it, educators adjusted textbooks, and the public reacted emotionally. Pluto wasn't just another space object to many people, it was familiar, even personal. So its reclassification felt unusual, almost like something important had been taken away. But after that moment, Pluto slowly disappeared from focus. It became a distant name in astronomy lessons rather than a world of interest. Until much later, when a new generation of observation tools, including the James Webb Space Telescope, turned their attention back toward the outer solar system. And what they found challenged long-standing assumptions. Pluto was no longer just a frozen remnant drifting at the edge of space. It appeared to be far more complex than expected. Early data revealed subtle signs of atmospheric activity, faint layers of haze and shifting patterns high above its surface. For a body so far from the Sun, this was unexpected. Scientists had long assumed Pluto's atmosphere would be extremely thin and mostly static, composed mainly of nitrogen with traces of methane and carbon compounds. But the observation suggested something different, a system that changes over time. A faint but active atmosphere shaped by seasonal and chemical processes. This raised an immediate question. How could such a distant, icy world still show signs of motion and change? The surprises didn't stop there. Surface images and infrared readings pointed to geological features that did not look ancient or frozen in time. Instead, some regions appeared surprisingly young. Smooth plains, shifting terrains, and unusual ice formations hinted that Pluto may not be completely inactive. One of the most intriguing possibilities is cryovolcanism, a process where slushy mixtures of water, ammonia, and methane rise from below the surface and spread across the landscape. If this is occurring, it suggests that Pluto may still have internal energy sources driving activity beneath its frozen crust. For a small object so far from the Sun, that idea is remarkable. It implies that Pluto may not be a dead world at all, but one still evolving in subtle ways. Even more intriguing are traces of organic compounds detected across its surface. These carbon-based molecules are considered essential ingredients in the chemistry of life. No one is claiming Pluto is alive, but the presence of these materials opens the door to deeper questions about chemical processes in extreme environments. Could slow reactions be occurring beneath the ice? Could hidden layers exist where chemistry continues in ways we do not yet understand? As data accumulated, Pluto began to look less like a frozen relic and more like a dynamic system with its own internal story. And then attention turned to something even more unusual, its largest moon. Pluto's largest companion, Charon, was once thought to be a quiet, inactive moon. A simple object locked in orbit. But closer observation revealed a very different picture. Its surface contains deep canyons, vast fractures, and regions shaped by ancient geological forces. Some areas appear reddish, likely formed through chemical reactions involving methane and radiation exposure. There are also signs that Charon may have experienced internal activity in its past, and possibly even now. One of the most surprising discoveries is how closely Pluto and Charon interact. Instead of behaving as separate, isolated bodies, they function almost like a connected system, exchanging material and influencing each other's evolution over time. Substances escaping from Pluto may deposit on Charon's surface, where radiation transforms them into complex organic compounds. This constant exchange suggests a dynamic relationship rather than a passive orbital pairing. Meanwhile, Pluto itself continues to raise questions through its unusual orbit. Unlike most planets, it travels along a highly tilted and elongated path around the Sun. For decades, this was considered a random characteristic of distant solar system objects. But newer studies have raised the possibility that something larger may be influencing these distant orbits. Some researchers propose the existence of a yet undiscovered massive planet in the outer solar system, often referred to as Planet 9, whose gravity could be shaping the motion of distant objects. Others suggest Pluto may not have formed where it currently resides. It could be a captured object from the outer regions of the solar system, or even an interstellar body drawn in long ago by gravitational interactions. These ideas remain unconfirmed, but they reflect how Pluto continues to challenge assumptions. One of its most famous regions, the heart-shaped plain known as Tombaugh Regio, adds another layer of mystery. Within it lies a vast, smooth nitrogen ice basin that shows almost no signs of impact craters. This suggests that the surface is being renewed over time, rather than remaining static for billions of years. Some scientists believe this region may conceal a subsurface layer, possibly even a liquid ocean beneath the ice. If true, it would mean Pluto has internal complexity far greater than once imagined. There is also evidence that this massive region may influence Pluto's balance, potentially causing shifts in its orientation over long periods of time, a process known as true polar wander. In simpler terms, Pluto may slowly reorient itself as internal mass shifts beneath its surface. As it moves through its long, elliptical orbit, Pluto experiences extreme changes in temperature and atmospheric behavior. When closer to the Sun, surface ices turn directly into gas, forming a thin temporary atmosphere. When farther away, much of this atmosphere freezes again and collapses. Yet observations suggest this cycle is more stable than expected, as if something is moderating the process beneath the surface. Even more puzzling, Pluto shows no clearly detectable magnetic field. This is unusual for a body that may contain internal heat or possible subsurface oceans. It raises questions about how small icy worlds generate internal dynamics, or whether Pluto behaves differently from anything we currently understand. In the end, Pluto's greatest significance may not be in what it is, but in what it represents. A world once dismissed as insignificant is now revealing complexity, activity, and mystery. Its story is a reminder that scientific understanding is always evolving. And thanks to modern exploration tools like the James Webb Space Telescope, we are only beginning to uncover what distant worlds are truly like. Pluto's journey from forgotten object to active frontier world shows one simple truth: the universe is far more alive and dynamic than we once believed. And even the smallest worlds may still hold the biggest surprises.